Ladies and gentlemen, welcome to lesson 12.1 for geometry. We are checking out some things about volume and surface area in this chapter, but this first lesson is all about exploring solids. A solid just being a three-dimensional shape, pretty much from what you know. So there's a lot of new terms here. Make sure you understand those terms by the end of this lesson. If not, go back and review in your book or review this video. So let's check it out. Let's see what we got. You are going to have to draw some things for this chapter. You don't have to be a professional artist to be successful at this. You just need to do the best you can and make it look halfway decent. So let's start off by defining this word, polyhedron. Very important word for this chapter. What is a polyhedron? So just like we had a polygon in 2 dimensions, we have a polyhedron in 3 dimensions. A polyhedron is just this. It's a solid that is bounded by polygons. So polygons we know from before, those are those shapes. In layman's terms, it's those 2-dimensional shapes that have all straight edges, all straight segments. They all connect at the endpoints, and that way you have a polygon. That's what you have as a polygon. So in other words, there's no curved sides to a polyhedron. And they enclose a single region of space. So you don't have these 2 separate entities. They're enclosing this single region of space. So that enclose a single region of space. And the plural for this, there's 2 different ways you can make this plural, polyhedron. You can say either polyhedra or you can say polyhedrons. You can put an S at the end. So you might hear either of those 2 terms. I thought I'd write both of them down here with you just in case you see either one. Okay, so let's now draw just an example of a basic, straightforward polyhedron. This is not a special type. But I want you to start off by drawing some vertices in here. Let's connect these vertices. And these don't actually have to be filled in like that. We're just going to let's just make a straight segment like that. If you drew in the dots, that's not a big deal either. But let's make first a trapezoid looking shape to start. We'll make it look like an isosceles trapezoid. It doesn't have to be that way, but this is a polygon right here. One of the faces, this is one of the faces, it's going to be a polygon. And now let's say another vertex of this was right back here. So let's draw a dot, draw your dot right about where I have mine, and we're going to start making some other parts of this. 3-dimensional drawings are a little tough for some students, but if you follow my instructions here, I think it should help out and help you draw some at least halfway decent looking shapes. So let's have our vertex here. Let's put another vertex up here. I'm going to make this the top face of the polyhedron here. And this is going to go at the same angle this is. So make another vertex right there. And then we're going to connect that here and here. And also here and here. So this is going to be the top of our polyhedron, this particular one. And then this spot where you had there a vertex, let's go up with that. And so that would be a quadrilateral here as well, but it's not going to be any particular type of special one. Let's make this, we'll go straight across from there, and then this coming down there, we're going to make a vertex right here. These ones you'd be able to see, these would be visible edges, and so those should be solid, and then this one here, connect this one, that would be dashed. And so from there, I've got a polyhedron. It's enclosing a single region of space. We have all polygon sides. There's no curved sides to this. And let's also take out our different color at this point. I want to label some extra things on here. So a face is going to be something like this part right here. Let's shade this in. This is right there. It's called a face. And right here is one of the vertices. This would be singular, a vertex right here. So So a vertex, there's actually a vertex here, 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 and here, and here. So that's a vertex. This is a face. One of, looks like 1, 2, 3, 4, 5, 6 faces on this. And right here, let's just thicken this part in a little bit. This would be one of the many edges that show up here. An edge just being something that connects two faces, or it's where they meet, where they intersect. Okay, so from there, let's move on and talk about, let's look at example 1. I'm sorry, that's not what I wanted. There we go. Example 1 here. Euler is not who I'm looking for. Hello, Bell. We'll talk about, there we go, we'll talk about this guy in a moment. But example 1, so here I'm not going to do examples like this in the notes together with you. I just want to verbalize this and talk about this with you. So decide whether it's a polyhedron. If so, count the number of faces, vertices, and edges. So you'll do stuff like this in your classwork. Let's just talk about it real quick though. I think it's easy enough just to talk about this. So is this a polyhedron? Yes. There's no curved parts to it. And you're counting the number of faces. It says 5 faces, so it's like this front part here, the back part here would be 1 and 2. You'd have 3 and 4 here and here, and then this bottom part here would be the 5th face. B, do you have curved parts to this? Yes, there's a curved part right here, and so it's not a polyhedron. You don't have to do the other part there. And C, do you have polyhedron? Is it all polygons along the sides? We have triangles around the lateral part of it. We have a hexagon base, so yes. So 7 faces if you count those up. Vertices, you would just be counting, like for part A, 1, 2, 3, 4, 5, and 6. So 6 vertices. 9 edges, if you count the edges, this would be an edge here, here, and here where they meet. You'd have another one here, here, and here, and then 1, 2, 3 right there. So that's the edges. That's how we would do problems like that one once you get to those in your classwork. But let's take a look now at some different types of solids. So we're going to take the pictures here, try to recreate these or draw these as best we can, and then decide which ones are which types as well. So up here, let's write in types of solids. And so which ones of these are polyhedra and which ones are not polyhedra? We're going to split this up into 2 different parts. Polyhedra, you could say polyhedrons. Either way is acceptable. But which ones of these have all polygon sides, no curved parts? Well, that would be this one right here and this one. So we're going to take these 2 and we're going to try to draw these over here. This happens to be a triangular prism because the bases are both triangles. It doesn't have to be a triangular prism. You could have a rectangular prism, pentagonal prism, whatever kind of prism you wanted. I'll show you a couple different ways we can draw this, but we do need to get some practice at drawing these. So to start drawing a prism, this is how I go about it. I draw a triangle, rectangle, whatever I've got first. I'm going to draw that right there for my base. Oftentimes I'll actually draw the rectangle first, so why don't I do that here. You could start off like that, but I'm going to start off instead with a rectangle right here. So from there, since I'm going to draw a triangular prism like they have here, instead of, you could have this stuff you don't have to draw, but this is just for your information here. There's a rectangular prism. That's still a polyhedron. You could have a pentagonal prism or a hexagonal prism. This one's going to be a hexagonal prism. You could have that sort of thing going on like that. Not my prettiest pictures, but these are all also fitting under here. They're just types of prisms. And so here I can draw my triangular base, and I can draw a congruent triangle as best I can. That one may be not quite exactly congruent, but pretty close. This one and this one should be the same. They should be parallel to each other in parallel planes, and then this would be a hidden line right there. You wouldn't be able to see that. But a type of polyhedron, or a type of solid that is a polyhedron, is a prism. And another one, the other one here, happens to be a square pyramid. When you're drawing a pyramid, I think this is the easiest way to go about it. If you're using pencil, you can continue this on. If you're not using pencil, this should be dashed. It's going to be dashed eventually. So if you're using pencil, you can draw in this next part here, and we'll erase parts of it here later. But go straight up from the center point of that, where these diagonals would cross, and you go up from there, draw a point, and then you're going to connect that vertex to all the other points here. And this one would be hidden. We wouldn't be able to see that one. So I'll make that dashed, and then I'd make these ones dashed as well. I'm going to make that a little smaller there. There we go. And so those lines would be dashed as well. So you'd have right there a pyramid. Alright, so these are the polyhedra, the ones that have all polygon faces. The ones that are not polyhedra are these other ones. These ones are parts that have, or polyhedra, they're solids, I'm sorry, they're not polyhedra, they're solids that have curved parts. And so with this, I think it's actually easier to start by drawing a circle, as long as you're using pencil with a cone. Draw a circle to start, and then go straight up from the center of the circle, draw a point up there. That's going to be your vertex. That is not my best work. Let's make that a little better. It's a little better there. Should just touch right there. And then since you used pencil on that, you can erase that, and this part would be hidden. You wouldn't be able to see that part there. So that's a cone. Cone just has a circular base, and they all meet at a vertex up towards the top. So all the sides would go up like that, just like you're used to seeing construction cones. It's the same sort of thing. It's that same idea. And we've also got cylinders. I think the easiest way to do that is to draw two congruent ellipses. These are representing circles, but you're looking at it on an angle, so you couldn't actually see the circular shape of it. But we got that. Tried as best as I could to draw those congruent. Not my best work again, but it's not too bad. It will suffice for what I'm doing here. I'll tell you, if you ever have to draw a perfect cone or cylinder or whatever, we'll come to that when the time comes. But for right now, just freehand as best you can. So a cylinder, two congruent circles, and going straight up and down, just like a soup can. You might see something like that. And now a sphere. So a sphere is a set of all points the same distance away in space from a center point. To draw a sphere, though, to represent a sphere on a piece of paper like we're doing here, you can draw a circle like that, draw half of an ellipse, and then the other half should be dashed because you couldn't actually see it. So that would be a sphere. So we need to be able to draw these at least so they're recognizable. It doesn't have to be perfect, but I should be able to tell what kind of shape is what. And a few definitions here. It's going to include a regular polyhedron. Just like we have a regular polygon, we have a regular polyhedron. And this is where all faces are regular polygons. And you may hear this called Platonic solids as well. So just, I think that's worth noting after this. Platonic solids is another name for that. And if you've heard of the philosopher Plato, it's actually named in honor of him or after him. So Platonic solids, we'll talk about what those are in a little bit, or what kinds you can actually make. But let's also define a couple more terms here. Convex polyhedron. Just like we have a convex polygon, the idea is really the same here. There's no parts that are caving in on themselves. A more technical way to describe that, though, is if you take any 2 points, excuse me, on the surface of the polyhedron, so on its surface, they can be connected by a segment that lies entirely on or inside the polyhedron. So that's the technical definition, but I think the way we'll be used to thinking of it more is there's no caving in parts. Okay, so just like concave polygons had no caving in parts, or had caving in parts, convex polygons have no caving in parts. The same thing applies to polyhedrons, 3 dimensions. And finally, a cross section. You need to know what that is as well. So cross section, that's the intersection of a plane and a solid. And so I think it'll help to look at the book just briefly. We don't have to draw this. I think just looking at it will be sufficient for this. But here's an example of a regular convex polyhedron. And so notice all the shapes are the same type of shape. They're all triangles, and they're all regular triangles or equilateral triangles right here. This is non-regular because all the faces are not the same shape. Here you have a rectangle. Here you've got this concave, what is that, 1, 2, 3, 4, 5, 6, 7, 8, this concave octagon for that side. Then you've got a rectangle here, you've got another rectangle here, another one here. These are not all the same like this is. And it's non-convex because you took 2 points here and here, you connected them, and that line, or that segment, did not lie completely on or inside the shape here. And so you can also see how it kind of caves in on itself. You've got this part caving in here, no part caves in on itself. And then down here some more examples. These examples are in your book as well, but just one more thing to mention here, the cross section. If you take a plane, imagine a knife slicing through the sphere here. This would be what you would see if you were to pull the sphere apart after cutting it. You would see this circular cross section right there. And so there's a few more examples here in the book. Notice you slice through it. Here you have a square as your cross section. You slice through it here, count the sides, 1, 2, 3, 4, 5. You've got a pentagon. Slice through it like this, and you've got this miniature triangle right there. So that should be helpful when you get to problems like that in your classwork, but we're not going to draw pictures like that. We're going to move on and write down this next. There are 5 and only 5. Pretty crazy that this is it. These are the only 5 regular polyhedra in the world. Polyhedra, polyhedrons. And again, these are called Platonic solids, named after Plato. Not the stuff you make shapes with or whatnot, the Greek philosopher Plato. Okay, so one of them is called a regular tetrahedron. REG standing for regular. And then these pictures, you don't have to draw these pictures. This is just to give us a visual of what it actually looks like. So here, what kind of faces do you have? Well, we've got 4 equilateral triangle faces. So let's write that down. 4 equilateral triangle faces. And you may recognize these shapes because we've likely done a little project to introduce this chapter, if you're in my class, to where we actually made these shapes. If we haven't done it yet, we'll probably get to it in a little bit. So another one, this one, a cube. It's also called a regular, and it's got 6 parts to it, just like a hexagon has 6 sides. A hexahedron has 6 faces as a 3-dimensional version of a hexagon. So this is a hexahedron is another way to say it, but generally we'll just say a cube. It's got 6 square faces. Remember, these are all equal sides. So this right here, here, and here is the same. All these sides, all these side lengths are the same here, just as they are here. These are all the same here, and so on. We could continue that with all of these. I won't do that though, because it's just going to start to get kind of crazy here. So a third one, would be a regular octahedron. It's got 8 faces that are all the same. Regular octahedron. And notice, yes, just like octagon, octahedron starts with the same prefix, that octa. We've got 8 equilateral triangle faces once again. A fourth one, this one, a dodecahedron, just like a 12-sided polygon is called a dodecagon. A dodecahedron has 12 faces that are the same. Dodecahedron. And this one has 12, and notice they are pentagons, so pentagonal faces. And technically I should say these are regular pentagonal faces, so they're regular pentagons. And the fifth one, the last one, these are only ones, only 5 in the world that are all regular polyhedra. So we have a regular icosahedron. It's got 20. Icos, that prefix stands for 20. So icosahedron is 20, and they're all equilateral triangles once again. 20 equilateral triangle faces. And so this is what you see in the book. So if you want to go and look on your own at the book and see a little bit more about those, you'll see these same pictures there in the book. We're not going to draw the pictures, we're just going to write down the information. This guy right here, he's giving us a stink eye a little bit, it looks like. This guy's name is Euler. It looks like Euler, but it's pronounced Euler. Think of him as does he look like a guy that would search for oil? I don't know. Maybe. Euler. This is Euler's theorem. So his first name is Leonard, but we're just going to refer to him as Euler most of the time. Euler's theorem. This is theorem 12.1. First theorem in chapter 12. It says this is true. So the number of faces, which we're going to refer to with a capital F, vertices, which we'll refer to with a capital V, and edges, and I just felt like putting his name over here. This is Leonard Euler right there. Edges E of a polyhedron are related by this formula, by the formula F plus V equals E plus 2. And then I remember this order because this is one of my fave formulas, my favorite formulas. And so if you spell the word fave, F-A-V-E, you've got everything you need there to remember it, hopefully. Remember the order they go in at least. Just take away the A. For faces, vertices equals edges plus 2. And so I'll try to use that as a mnemonic device to help you remember the formula. Favorite formula here, so fave, F plus V equals E plus 2. We're going to use this formula in our example 1 coming up next. So let's take a look at what that says. So let's say that a solid has 10 faces. We don't know what this solid looks like yet, but we do know that it has 4 triangular faces. So 4 triangular faces, 1 square face, 4 hexagon faces, and 1 octagon face. I could say octagonal, hexagonal, I'll do that. So hexagonal face is 1 octagonal face. And we're going to try to figure out how many vertices the solid has. How many vertices does the solid have? Excuse me. Getting over being sick. Yeah, it's happened more than it should this year. I'm getting sick. Not good. So what do we know? We know this right here. Let's put this in our different color. Circle this up here, that this is your F value. This is your faces. So we know that faces, F value equals 10. Do we know the edges? No, we don't know the edges yet. Do we know the vertices? Don't know that yet. So we know this at least, but we don't know these two. However, we know that they're related in this way, that F plus V equals E plus 2. Pretty cool. Thanks, Euler, for proving that theorem. Pretty amazing that that always works out that way for any polyhedron, but it does. We're not going to go over the proof. It's beyond the scope of this class, but it will work every time. And we can thank Euler for proving that it works every time for us. So to find the total number of edges, when you come to a problem like this, they're a little trickier. We have to think about it like this. Total number of edges, E. We should consider this. Think about these shapes, these faces coming together. So wherever you have a face coming together, the two edges of the face will come together to form one edge. So if we think back to this, notice this square comes together with this square and it forms one edge together right there. So if you've got 4 edges to a square, but each one of those edges is going to join another edge, we're basically going to be taking the total number of edges for each of the shapes all added together and then dividing that by 2, because each edge will be shared with another polygon. And so let's do that here. Let's make our little table here. So again, I'll reiterate what I had said there. It might be a good idea to go back if you didn't understand what I was saying about the two edges coming together to form one edge, meaning that we'll divide our total number of edges in the end by 2. Go back and review that as needed. Also, you have 4 triangles. In this one, let's put the total, or the number of edges for each one. That'll be our first column here. So in other words, for each triangle, you would have 3 edges. Then over here, let's put our number of edges for all of them. So if you've got 3 triangles, but you have 3 edges per triangle, but you have 4 triangles, we're going to take 4 times 3. So if you don't draw this off to the side here, but this is just to help you visualize what's going on, notice each one of these triangles has 1, 2, 3 edges. And we have 4 of those triangles, so putting them all together, 1, 2, 3, 4, we're going to have 4 times 3, which is 12 edges right there. And if we have the rest of them, we have 1 square. That would be 4 edges for each one. And there's only one of them, so we just have 1 times 4, which is 4. We also have hexagons and we have octagons. So how many hexagons do we have? We have 4 hexagons. And we only have 1 octagon, so we'll put that down here. Number of edges for each hexagon is 6, for each octagon is 8. However, we have 4 hexagons and only 1 octagon. So we have 4 times 6, which would be 24 edges for all the hexagons put together. In the octagons, we'd have 1 times 8 would just be 8. So here, if we take the total of all these, 12 plus 4 is 16. 16 plus 24 is 40, and 40 plus 8 is 48. So this 48 is the grand total for the edges, but however, we have to think about this. So this is the grand total. It's not our final number for E, because remember, each one of these, we've got to put these two together, here and here. We'd have to put, if you had a hexagon or a square coming together with a hexagon, you don't have to draw this. I don't want you to draw this actually. But if you had something like that coming together, yes, there's an edge here, and yes, there's an edge here, but when you put them together, when you join these together right here, this edge and this edge will come together and just make one edge right there. So you put them together, those two edges become one edge. So we have to take this number because of that and divide that number by 2. So let's write that out in words here so that it'll make sense when we look at it later. So since in a solid, each side or edge is shared by exactly 2 polygons, there are, in this case it was 48, but we divide that by 2 to get 24 for the edge number. So 24 equals E, total edges. So that was the harder part. We've got our E value now. We know what our F value is, the faces, and I remember the formula. It's my fave 2 FV equals E plus 2. So fave 2 formula, we are taking F plus B equals E plus 2. So we're going to say, let's write the formula out first like that. F plus B equals E plus 2. And then plug in the values that we know. We know that F is 10. My vertices I don't know yet. That's what I'm going to solve for. And I know that E is 24. So from here I've got 10 plus V equals 26. Let's use our different color for this final step here. Subtract 10 from both sides. And that leaves you with V equals 16. So you have 16 vertices for your value for V there. So if you were to draw an actual shape that looked like this, I'm not going to try to do that here, but if you had all these different types of faces, you got 10 total faces, and you were to actually count the number of edges and vertices that it would make if you had a shape like that that all came together to form one polyhedron, you would have to have this many vertices and this many edges as well. Just before we finish here, I'm going to take a look at examples 5 and 6 in the book. We're not going to do ones together like this, but just wanted to point out that, hey, there's some pretty cool applications to chemistry here. We talk about molecular structures, molecular bonds, on how they come together. Euler's theorem can be applied to that, so neat little example there. You might do something like that in your classwork as well, so check that out. And if you like soccer, maybe you've never noticed this, but there's actually polygon faces. Yes, it is a sphere generally, but the faces themselves are polygons. And so if you think of it as a polyhedron, these being the faces, you can apply Euler's theorem here again as well. F plus V equals E plus 2. So let's go back to the notes here, and that's it. I'm not going to do any more examples with you. So you've seen those examples. Use the examples in your book though too as well, and hopefully you'll find that helpful. And maybe you should, I've actually got some of these. I'll show you real quick. So here we are. Here's my tetrahedron right here. Right there. Tetrahedron. Pretty cool. Cube. These are all dice. I got these off of Amazon. It's got 6 sides there. Octahedron. This is a fair 8-sided die. The chance of it landing on each number is the same. Here's a dodecahedron. It's got 12 sides to it. And finally, the icosahedron. 20 sides. Where's number 20 on there? Can't find it. Where are you? 20? There it is. There's 20. So 20 sides to an icosahedron. Peace. I'm out.